Hello. Professor, we are on live.
Yes. I'm also live. I'm also present, but I don't see any students right now. So does it actually get posted even if it is not live? Even if it is right now, it's on YouTube.
It will be straight away posted, sir.
Okay. Yeah, right now I don't see, I can see the link, but I don't see any student on this. So we will wait for some time. If there's no student who has joined on this, then maybe we can consider removing it from YouTube. Huh?
Okay, Professor. Anyway, I
Yeah,
have
because
started.
yeah, because it makes no sense to just need to just
Yeah,
stare at the
sure.
screen for some time. So maybe we'll tolerate for like 10-15 minutes.
Yeah, sure, Professor.
Yeah. I'm right here. I'm just muted, but I'm there. Huh?
Yeah, sure. Okay, thank you.
Hello, Sai, can you hear me? I can see
Yes, sir.
Samudra Purna Sai.
Yes, sir. Good morning, sir.
Good morning. Good morning. Yeah. You can go ahead and do you have any questions so far? Which week are you? Which week have you recently watched?
Sir, is capillary rise is equal for same curved surface and straight surface? That means straight. If a tube is placed, if here we are taking a straight surface, no, sir. If there is a curved surface, is there any effect of surface tension on that curved surface on the capillary rise?
Here, did we take a? Okay, so was the analysis based on 2 dimensions?
Yes, sir.
No, we have the analysis that analysis that was this is for the benefit of viewers who may not be seeing it. I'm guessing you are referring to the week 6 lectures on dynamics of capillary rise, correct?
Yes, yes, sir.
In the dynamics of capillary rise, we have looked at a tube.
Yes, sir.
It's not 2 dimensions. It's a tube.
Oh, it's a tube of
Should I
axis symmetry.
share? Yes, it is axis symmetry. Yes.
Yes, sir. I am asking the question here. We are taking the tube of straight. That means there is no curved surface. There is no curved surface, no, sir. In the tube, there is no. That means there is no like YouTube. There is no inverted YouTube or curved surface of the tube. If there is curved surface.
Okay. See, I'm getting confused. When you say curved surface, the tube is a curved surface, right?
If the cube is of curved surface, is there any effect of curvature tension on the curved surface, or is there any in the?
No, are you referring to? No, I'm saying the tube is already curved surface. The analysis has been done for a straight tube. Is that what you're trying to ask? A
Yes, sir,
straight
yes,
tube
sir.
versus, let's say, a bent tube. Okay.
Yes,
It
sir.
is because it's already a curved surface, so I couldn't understand. All right, yeah. So the analysis was done for a straight tube.
Yes, sir.
Okay.
Yes.
The analysis is obviously not valid for a bent tube because one needs to do the in many cases it may not be even possible that easily to do it for an arbitrary bent tube. But I see no reason, if you ask a general question like will surface tension be valid, I see no reason why it could not be valid. If you have let's the problem essentially, let me just share my screen. Can you see my screen now?
Yes, sir.
Okay, so the analysis has been done for dynamics of a capillary rise. This has been done for a straight tube.
Right.
So if you have a tube which is bent later on.
Yes, sir. Bent later on
Meaning-
or starting only?
Starting only, I'm unable to imagine. What do you mean by starting? Let's say it's bent right here.
Within the length H, if there is a bend what happened to the capillary rise, effect of the capillary rise?
So it is of course not straightforward to give a complete answer, but I'll give you a partial answer. Okay. If you look at if you've gone through the internal analysis, the analysis has been, the ultimate goal is to get some kind of a curve like this. Okay.
Yes, sir.
And to get I first started by basically making a guess of what should be the various shapes that we should expect. So inertia for very, very short heights, meaning for heights much smaller than the final height h, the fluid would rise through the capillary tube with inertia being dominant force. Okay. And even if there is a bend, if there is a bend in the tube beyond that inertial height, it will not matter. Initial rise will still be the same.
Okay.
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 So
Okay.
I'm trying to make you think of something like this. For example, this is your water level, and you have a
Yes.
tube which is like this.
Yes, sir. Yes, sir.
So in the initial phase where you have, it should not matter. In this phase, it should be completely dominated by inertia.
Okay, sir.
And even subsequently, it all depends on where does you could continue to have this rise, but then there may be a point where, as the tube is rising through this here, there may be a point where the fluid may rise even in the second state. Okay, the second stage. Okay, so if you've basically gone through, if I basically finally go to the last thing here. So this is initially you have an added mass effect, then there is an inertial rise, and there is an early viscous rise. It all depends on where the bend starts appearing, as you said. If it's initially a straight tube and a bend, it all depends on where the bend starts appearing. But I really don't see why the initial part of the analysis should be very different. I think the initial part of the analysis will be unaffected.
Yes, sir. Inertia will be unaffected, but viscous region will be affected. If there is a bend in the
yes, but again, it is we also have to understand how will the viscous region effects be affected. For example, if you looked at the analysis, we calculate the shear stress at the wall because the fluid is actually rising through it, but then it's also experiencing a viscous resistance, and we have estimated the viscous resistance. If you see here, the F mu that we estimated here, this F mu has been simply said to be 2 pi a z times tau mu or tau nu. This tau that is there, this is the viscous stress. Is calculated by assuming that the flow is fully developed, and it is also a parabolic velocity profile. So if the tube is very long and bent, and the overall curvature of the bend is much larger, the radius of the curvature of the bend is much larger than the radius of the tube, this analysis would still be valid by and large.
But you may have to replace this Z. Z is here, the height of the tube, remember.
Okay.
Okay. So this is in FMU basically tells you how far has the fluid risen through the tube as it's rising. Okay. But if you have a bent tube, then instead of basically Z, you may have to take this length along the tube.
Okay.
You understand?
Yes, sir.
I mean, that would be one way to attack this. To be honest, I haven't done this analysis for a curved tube, but that would be the direction in which I would think.
Okay.
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 This 2 pi a z is really the inside surface area of the tube. But this is only valid for a straight tube. If you have a curved tube, then you'll have to take into account that the tube is actually curved, and you have to account for the length of the curved tube.
Okay.
Okay.
If there is a curved surface, means then the effect of the surface tension is also we need to consider, no, sir?
Effect of surface tension should not be effect of surface tension also, if you understand here, when it comes to the curved region. Now, for example, over here, the surface tension force has been simply written as 2 pi a gamma cos theta. What is 2 pi a gamma cos theta? Basically, there is a contact line over here at the top. Can you see my screen?
Yes, sir. Yes, sir.
Okay, there is a contact line here, and what is the shape of this contact line? It is a circle.
Yes, sir.
This contact line is a perfect circle. What is the radius of the circle? It is a.
Oh.
Okay.
Okay.
So imagine if you have a tube locally, it is like this. The tube is basically inclined locally.
Okay.
Okay. And
Yes.
now you have an interface like this. The angles
Yes.
here and here will be different.
Yes.
Just coming up, determining the surface tension force will be itself tricky, because the contact line is not a circle. It's basically a three-dimensional curve, this contact line, because it's basically on this boundary. Okay.
Yes. Yes, sir.
The analysis will still give, this analysis that we've done for a vertical tube will still give you insights on how to think about a curved tube, but it may not be analytically possible to do it for a curved tube,
Okay.
an arbitrary curved tube. Okay.
Okay.
Yeah, but it's an interesting question. Yeah, several terms do change. Surface tension force will be modified. So I would like you to sort of look at these force balance that we've written down and ask yourself, what are the things that change? Okay.
Okay.
Pi a square z here, that's a gravity term. Pi a square z is basically the pi a squared z times rho is the mass of the vertical column. But if this term will still contain z is still the z should not change, because the weight of the vertical column should not matter for gravity. Okay. So that I think should not change. Here you will have to z dot is basically the local velocity. But if it's passing through a curved tube, the velocity orientation will not be along the vertical, will not be just z. It will be along the axis. So it will be like, it's not z dot, you may have s dot square. S is basically the arc length. So it will be s dot will be the velocity.
Okay.
Okay. That's what because if s is the arc length from the bottom.
Okay, sir.
Over here as well, you'll have 2 pi a times s. Yeah. So where are you studying, Sai?
Yeah, NIT Durgapur. I am from Andhra only. I am here. I am studying MTech in NIT Durgapur in fluid mechanics in heat transfer specialization.
Okay, NIT Durgapur. Good to hear that.
Sir, in the force wetting and coating flows.
Force wetting?
In the force and coating flows.
Okay.
in the boundary, in the Navier-Stokes equation, in the boundary condition of non-dimensional form. Here we will get the non-dimensional form.
I'm just scrolling down the lecture. Please stop me where you see you can point me to the right place.
Yes, here only.
Okay.
That the last term we get in the last, that means here we get multiply throughout by CA up. We get that means first one for RE into du bar by dt is equal to minus del star P nabla star P. Yes, sir, that equation.
Okay. So are you referring to this equation here?
No, sir.
Or the first or the previous one?
Yes, sir.
Oh, sorry. I think let me just do that again.
Yes, sir. Here.
This equation here.
Yes, sir.
Okay. So what's the question here?
Here I got the last term as bond number by capillary number, sir.
Okay. You got a bond number there.
Yes, sir. Bond number.
Okay. What was the formula for the bond number?
Bond number formula is.
I'm asking you, what is the formula that you got? You have got a bond number, right? So what would the bond number?
1 minute. I do this analysis. Sorry, another page.
Say bond number will be the ratio of
Gravity force by viscous force.
No.
Surface tension force. Gravity force by surface tension force.
No, I want to know what did you actually get. So
Rho G LC by gamma.
So you got rho G LC by gamma. This is what you got. Sorry, I'm just using my mouse pad to write the thing. But I hope you can see this. Okay. Rho G LC by gamma. But this is 1, isn't it? Because LC, it's if you substitute the expression for LC. So LC is what? LC is nothing but okay, there is some rho G LC square you should have got, right?
Rho G LC square by gamma.
So what if you substitute the expression for LC is the capillary length. If you substitute the expression for LC is square root of gamma, LC itself is square root of gamma by rho G. So you are absolutely right that you get a bond by capillary number, but this is a case where bond number equal to 1. Okay. Did you get that, Sai?
Yes, sir. Yes, sir.
Okay. So, but it leads to an important question. Why did we get this? The reason we get this is because we have chosen the characteristic length scale for non-dimensionalization as LC itself.
Yes, sir.
When if you instead of basically choosing the characteristic non-dimensionalization LC, you have chosen some other length. Let us say you have chosen some R for case of just a discussion. If it was R, then what you would have actually got is instead of LC here, I'll write it with a different color. You would actually get R square. Is this clear?
Yes, sir.
So, but because we chose LC as the characteristic length scale, bond number is, as you said, rightly said, is a ratio of surface tension force to gravitational force to surface tension force. But LC, the capillary length, is also the length scale that emerges where surface tension and gravity are exactly in balance.
Okay.
And that's the reason bond number is exactly equal to 1, which means that at the capillary length, bond surface tension and gravitational forces are in balance,
Okay.
are of the same magnitude. So if you are at a, as you would have seen in the course, if you are at a length scale much larger than the capillary length, then surface tension becomes less and less important and gravity becomes important. If you're at a length scale much smaller than the capillary length, then gravity becomes less important and surface tension starts dominating.
Okay.
But when you have chosen the length scale to be the natural length, capillary length, you get bond number equal to 1. Is that clear?
Yes, sir.
Okay. But I'm very glad that you have actually gone through the analysis and done this. This kind of a doubt will only come when you actually work it out yourself. And I'm very pleased to see that you have done that.
Thank you, sir. Sir, and I want to ask the assignment question answer, assignment answer for every week. That is
Okay,
not
so
uploaded in the.
we have only given the choices, right?
Yes, sir.
Okay, so I will which can you be specific about which assignment you want?
Assignment 6, sir.
Okay, I will ask the TAs to upload the assignment solutions as well. Huh?
Okay.
Yeah. Okay.
In assignment 6, I want to know the how we are equating the gravity forces to the, that means in the assignment here also
Let me open that. Let me open that. Give me a second. I will ask the TAs anyway to share the assignment. Okay, they will. Can you see the screen?
yes, sir.
Yeah.
Yes, sir.
Which specific question are you referring to?
Fourth question. This question only, third question, sir. Third question.
Okay. Okay, this is for a higher capillary number. Okay.
Yes.
Okay. So I'll ask them to share the solution for this. I believe the answer is D.
Yes, sir.
I'll ask them to share the solution for it. I should be able to show you how to get this as well. All right, I'll ask them to share it. Share the solution. It's fairly straightforward. To work out the case where the capillary number is large, not small. You can't basically the way to do this is the way to think about it is you have basically two regions. We have a static meniscus where you have the natural length scale is capillary length, and then we're introducing a dynamic meniscus, correct?
Yes, sir.
So when we are doing that, it's all about basically trying to determine the length scale of the dynamic meniscus.
Yes, sir.
Okay.
Yes, sir.
In the analysis that we have basically done, the length scale of the dynamic meniscus represented with the alphabet small l. Okay.
Okay, sir.
The length scale of the dynamic meniscus was shown to be capillary power 1/3. Okay.
Yes.
That will change. Okay.
Okay.
So I'll ask the TAs to share the solutions. Huh? Yeah. And you
Sure.
look at the solutions, and then when we come back to it, you can basically again raise this question in the next class, and we will discuss this.
Okay.
Yeah.
So, can you please explain the transition of static to dynamic meniscus, the concept of the same lecture?
Okay. So I'll just let me again share the screen. Which particular part you want? Okay, here.
Yes, sir. Here.
Okay. So yeah. So go ahead.
Yes, sir.
Go ahead with your question again.
That means I am not clearly understanding how we are doing the scaling analysis. That means discuss how we, that means transition from static to dynamic. Here, how we are doing scaling analysis by employing the lubrication approximation.
Okay, but did you first understand why there should be a transition region?
No, sir, that is the problem. Why there
Okay,
is
so let's imagine the following. So there is you can understand that there are several ways to think about this. The simplest way I like to think about it is the very reason there is a coating in the first place is because viscous effects are basically dragging the fluid up. Okay.
Okay.
So they're very close to the plate, it is viscous dominated. Okay.
Okay.
But if you go very far away from the plate, the very region you have viscous forces is because there is motion. Viscous effects cannot be, you cannot feel viscous forces till you generate motion in the fluid. Okay. But very, very far away from the plate, the fluid basically simply couldn't care about the motion of the plate. So very far away from the plate, horizontally away from the plate, you should expect that the fluid will largely remain at rest.
Okay.
So therefore, if the fluid is at rest, if let's say if the fluid were completely at rest, there was no plate motion at all, then even then there is a meniscus, and that meniscus we refer to as the static meniscus. What's the logic for the static meniscus? The idea is that you have a flat interface in the far field, but when it comes to the plate, it has to satisfy a certain contact angle boundary condition, as I'm trying to show here. That is the orange dash curve.
Okay.
Now what you have to do is you need to weigh, if the moment the plate is in motion, then it is very close to the static meniscus far away, because the effect of viscous forces are not felt that far away, but it has to transition to a viscous dominated region.
Okay.
So not only the interface bends this way, the nature of the forces also changes. So if you have viscous dominated in the very close to the plate, but if you have a balance between gravity and surface tension far away,
okay,
there has to be a point where viscous effect starts balancing surface tension.
okay, okay.
Okay. Now, so this is the case where you should expect, and where should this occur? This should occur where you are neither very close to the plate, which is fully viscous dominated, and gravity is not important, and the interface is flat. If the interface is flat, again, there is no surface tension force because there is no curvature. Or it should not be so far away from the plate that there are no viscous effects at all. Okay, because there it's completely static region. So you should expect that wherever the interface is bending, there should be a transition not only in the shape of the interface, but a transition in the balance of forces. The transition and balance of forces is where you actually now have viscous effects are trying to pull the fluid up.
Okay.
But while the viscous effects are trying to pull the fluid up and cause the coating, it is being opposed by two forces. What are the two forces that are opposing the viscous forces?
Surface and gravity.
Surface tension. You can think of why surface tension would oppose, because in the process of coating, you've created an enormous surface area.
Okay.
You also created a huge curvature in the interface. So surface tension would oppose. So does gravity, because you're trying to drag the fluid up, and gravity will oppose it.
Okay.
Correct?
Yes,
So
sir.
that is basically, so therefore there has to be a competition. The understanding is that if you're far away, meaning when you go far away to the right, its gravity starts dominating over surface tension and makes the interface flat. But as you come closer and closer to the plate and you follow the static meniscus and fall below the capillary length, if you go below the capillary length, then surface tension becomes important below the capillary length. So now you can imagine that there is a balance between surface tension and viscous forces. That region is referred to as a transition region. Okay. So this figure, if you actually see, is not to scale at all. It's not at all to scale. Okay. So you can imagine that there will be a static region. You can imagine there is a static region somewhere in this very small shaded region in yellow that I'm showing, where you actually deviate from static to the coating thickness. Okay. Now, so you basically say that there is a static meniscus and very close to the plate in the transition region, you start deviating from the static meniscus, and that is what we refer to as the dynamic meniscus. Okay. The dynamic meniscus, as it turns out, if we are employing lubrication approximation, and lubrication approximation essentially says, reduces to the fact that the vertical length is much larger than the horizontal length, meaning the thickness of the film in the transition region is much smaller than the length over which this transition region occurs. Okay. So in other words, you can see very clearly when we do the analysis, we are essentially saying that this reduces to the fact that variations in X, variations in X, which is along the vertical plate, variations in X are much smaller than variations in Y. Okay. This is simply because of two very different length scales. This is the kind of analogy that you would have employed even when you've done, let's say, if you've done a course in boundary layer theory. Even in boundary layer theory, the diffusion terms in the horizontal direction of the boundary layer. So let's say if this was a boundary layer over a flat plate and you have in parabolic profile like this, the diffusion in the horizontal direction, that is del square u by del x square, is much smaller than the diffusion in the vertical direction. But now all that we are doing is we are now rotating this diagram by 90 degrees and also changing the direction of the velocity. So now for us, it's a bit like there is a vertical plate and there is an interface here, and the velocity is basically the velocity is this way. So you can imagine, you have to think about rotating the second figure, rotating this figure by 90 degrees, and also changing the direction of the velocity. Okay. But the argument still holds. The large variation in the length scale, if you can arrive at this by simply looking at writing down the full equations. You're writing down the full equations of motion. Here both the terms are present. The two terms are present. Okay. The derivatives in X and derivative with respect to Y. And if you say that there is a massive variation in the length scales, then the horizontal derivatives in this case as del square u by del y square actually dominate over the vertical derivatives along the plate. Now with that, it allows us to basically simplify the equations, and we can actually again check whether the results are consistent with what we have assumed. The thickness scales like capillary to about 2/3, whereas the dynamic meniscus L scales like capillary 1/3. So you can imagine that if capillary number is very, very small, capillary 1/3 is much larger than, so capillary 1/3, sorry, sorry, again I made a mistake here. Yeah, capillary 1/3 is is much, much larger than capillary 2/3. Got it?
Yes, sir.
That is simply that is a consequence of the fact that capillary number is very small.
Okay.
Okay.
Yes,
So again, it suggests that the vertical length that we have taken, the vertical length over which the variation is occurring is much, much larger than the horizontal length, the thickness in the in the transition region. So this figure is not at all to scale. Okay.
okay.
But please do watch the lecture, and I have discussed this again in detail.
Okay.
Yeah. Anybody else? Himanshu, Himanshu is here. Himanshu, any questions?
Sir, on the same slide, when you were explaining, you said that this coating problem is subject to scale separation. I just wanted to clarify as to what do you mean by when you say scale separation. What exactly
So
does
there
this
is.
term mean?
So you are dealing with two very, very disparate scales here. There is a coating thickness, which is H infinity, and there is a macroscopic length scale in the system, which is the capillary length, LC. So there is the coating thickness is much, much smaller than the capillary length.
Okay, sir, I got it. Got it. One thing I wanted to ask from
Yeah, go ahead.
sir, one thing I wanted to ask from one practical perspective. So
Yeah.
you showed us a video of capillary rising in the dynamic. So in the next, I mean the dynamic capillary rise, you showed this video in which there was a capillary which was rising, and then you said that we see that since the boundary layer develops very rapidly, so after that we consider it to be fully developed for the most of the length. So in such big pipes, that is okay because we can actually see the velocity profile by injecting the dyes. But here, when the capillary is very small in diameter, so if we wanted to validate this argument experimentally, so how do we? I mean, how did people experimentally validated this by saying like when it was rising, fully developed was observed all of a sudden?
So okay. Okay, I think the question that you are asked is very important, but one should look at let's look at it in a more broad perspective. So this is not just for this particular problem, but it is true for any scientific theory. I'll tell you how one of the ways in which we build scientific theories is by saying that we have to start making guesses. Okay. As the great Richard Feynman basically explains in once, which you'll find this video on YouTube. If you want to build a scientific theory, you first make a guess. Now here, one of the things that we're trying to do here is we're making a guess about what are the assumptions that I can make. What are the best assumptions I can make? Okay. Now, it is possible that the flow may not be fully developed. Okay. Let's say you suspect that the flow is not fully developed. Now, there are some conditions that you will employ. What are the requirements for a fully developed flow? So you can actually say you look at the entry length region. If you do a flow in a pipe, long flow in a pipe at high Reynolds number, as you would have, let's say, done in a course on boundary layer theory, you figure out what is the entry length. Entry length will scale with the Reynolds number of the problem. Higher the Reynolds number, longer is the entry length, which means that longer it takes for the flow to convert from a uniform flow to a fully developed flow. If the Reynolds number is very small, you would expect that the entry length is very, very short. So therefore, you would hit the fully developed condition much sooner in time, and not just in time, much sooner in length as well along the pipe. That's the first argument. So it is reasonable to make an assumption that the flow is fully developed fairly quickly, but you can actually come up with some numbers, okay, based on what you've learned from boundary layer theory and others, okay, similar theories. But another thing you can also do is you say, let me go ahead and make the assumption that the flow is fully developed. Such an assumption is meaningful if it allows me to go ahead and make some predictions. But the prediction, you can go ahead and test the original assumption by doing experiments. Is the flow fully developed or not? But that may be very hard to do. But an easier thing to do is to just put a camera and check the position of the interface. How did we get the position of the interface versus time, meaning Z of t? We got by making these assumptions. The flow is fully developed. So in a certain region, you check whether the flow is it rising like Z, does Z go like t power half? That is something that you can make it's easier to test than going ahead and checking whether the flow is fully developed. Because to determine whether the flow is fully developed, you will have to basically do some kind of imaging like particle image velocimetry, okay, in an experiment. So you don't directly test the assumptions that have gone into the theory, but you actually test the predictions made by the theory. And if the predictions made by the theory are perfectly valid, it is fairly good or reasonably good, then you stick to the theory. Okay, there is no reason to abandon the theory. In fact, I would even go ahead and say that even if the assumptions are not perfectly valid, but the theory is still doing well, it's still worth keeping the theory because it makes some valid predictions. But if you have strong evidence to suggest that the assumptions of the theory are invalid, rather than straight away abandon the theory, you start modifying the assumptions and start building a better theory. Himanshu, were you convinced with that argument?
So sir, we are making an assumption, then we are finding the consequences, and then we are saying since these consequences match the original one, so the theory is valid.
If you fundamentally think about it, most of the theories are like that. Now the cleverness of the theory comes by how are you able to make the assumptions. There it requires the assumption, and it's not that assumption is like assumption is a very clever guess. To figure out what are the right kind of assumptions that I have to make so that I can keep the essential physics of the problem and get to the answer is where creativity in science comes in.
Yes, sir. Got it, sir. Got it. This there is one question I want to ask about that. When we were writing the forces which are for the conservation of momentum, in which we write f of gamma plus minus f of g minus f of mu minus f of t, in which you said that pressure force is one of the opposing forces. But when I look at it, I mean very clearly. So there is a surface tension because of which the pressure just inside the meniscus and just outside the meniscus is having a difference, so that there is a force. But sir, when we look inside the meniscus, the PA was less than PB, and every time it rose, the PA was getting lesser than PB. So why is the pressure force the opposing force? Then it should be a supporting force, shouldn't it be?
So
sir,
if you
here only, sir.
Am I looking at the right thing according to you?
Yes, sir. Yes, sir. So
okay.
Here, sir. Yes, sir. Here only.
Okay. So if the fluid is traveling with a certain speed, this is basically coming from a Bernoulli kind of argument that a fluid traveling with a certain speed will have a lower pressure.
Yes, sir. That is the point. So the point where the fluid is being sucked in, it has a pressure, let's say PB, and where it is rising, so PA has a velocity. So PA is rising, so PA has a velocity. Then there the pressure is lower, and the pressure at the bottom is higher, and that is what we are trying to have, the negative pressure gradient in the direction of flow. So it supports the flow. So why are we saying
I'm
that?
just trying to understand.
So there was one diagram.
You're referring
in
to
which
PA and PB.
yeah.
Wait, give me a second. Give me a second. Which figure are we referring to? You're referring to PA and PB. I'm trying to find out what is this PA and PB you're referring to.
Yes, sir. So is on the similar basis when we wrote like PA and PB. So A is rising, B is constantly on that. So in that figure, it is just one. This is just I think one lecture back. Just before that,
Okay,
capillary.
Give me a second. Give me a second. Give me a second. I have not anywhere written PA and PB.
So before the flexible surface, when we were actually discussing the static meniscus.
I still don't see that figure that you're referring to, PA and PB.
Sir, during the static meniscus, before earlier weeks, before this one.
Okay, so that's not even the earlier meniscus. Okay. Okay, I think you're referring to week 3.
I have drawn the photo, sir. I mean the pictures, so I can show also.
Yeah, please do.
Sir, here is this one, this photo.
I can't see. Where's okay, you're
sorry,
drawn it on a piece of paper. Let me just see if I can.
This one, sir.
Okay, let me just pull that out. You're saying I made this kind of a figure.
Yes, sir. So here this was PA and P0. So P0 was higher than PA.
Okay, so before the okay, let me just share that again. Okay.
Yes, sir. Here only also we can see, sir, in any diagram. Yeah, here.
Okay.
Sir. So here,
yeah, sorry.
sir.
Now.
Sorry, sir. Sir, this is so so we can see the meniscus of the which is rising in the capillary, and there is a point. There's a point from which this fluid was entering. So so if we say that the point just inside the meniscus in that capillary tube is point A, and the point B is the point from which the fluid is entering. So here is A and here is B. So
A is over here.
Yes.
A is
yes, sir, yes.
A is here. This
yes,
is A.
Sir, yes, sir. Yes, sir. And here is B. So the pressure at A is definitely lower than the pressure at B.
But
when
you have to remember that you are referring to this pressures difference in the pressures purely because of hydrostatics, okay, and curvature effects.
Yes, sir. Yes, sir. Both
But
are both.
yeah, but then if you start thinking about the fluid actually rising up, then the pressure, because fluid is entering at the bottom with a certain pressure, with a certain velocity, you should expect that as it's entering the fluid at a certain velocity, its pressure is its velocity, because of velocity, its pressure is lowered. That's dynamic pressure. Got it?
Sir, that same dynamic pressure would be at A also, because A is also rising when the fluid is entering. So from the argument we made when we were dealing with when we show that boundary development, so that is what. So if there is a dynamic pressure at P, then there should be a dynamic pressure at A also, because the A does not have zero velocity. A is also moving up. And actually, and actually, sir, A is moving up with a higher A is a point at the, if it is at the center, then the velocity is also higher, because that profile is then parabolic. So it would be a higher 3/2, 1.5 times more velocity at A.
No. The mass balance says that whatever rate at which fluid is entering at B is the same velocity at yeah, you shouldn't be strictly applying this idea of the velocity profile being the fully developed profile here. You should not be applying right below the meniscus there. Okay. The fully developed profile is applied in an average sense. Okay, that's the first one. Otherwise, you should expect a bulge in the middle, not a depression. Okay.
Yes, sir. So even if we consider the on an average sense velocity, but the velocity would be same in an average sense then. So dynamic pressure.
So see, surface tension is trying to pull it up. Correct? Surface tension is trying to pull it up.
Yes, okay. Sir. Yes, sir.
But that is what is making the fluid rise up. But you have a higher pressure on the outside, which is the atmospheric pressure. Okay. And just below this, you have the pressure at A, which is lower. Okay. Pressure at B is even higher than A because of hydrostatics. Okay, because yes. You have a rho G, pressure at B is pressure at A plus rho GH. Correct?
Yes, sir. Yes, sir.
So now what we are trying to say is that when the fluid basically rises through the meniscus, because of the very fact that its pressure is actually lower than what it would be if we do not consider variations. Okay, because of velocity, if we do not have velocity at all, then the pressure at A and B and above can be simply related by hydrostatics and surface tension. Correct? But the moment you basically have fluid in motion, its effective pressure has decreased. And because its effective pressure has decreased because of its motion, atmosphere will be able to basically do a better job at pushing it down. That's one way to think about it. See, atmosphere is trying to push it down. Okay, that is P naught. Okay, now you are saying that this particular column, okay, its pressure is actually slightly lower than what its value would be when it was stationary, because of its very act that it is moving with a certain speed. Its pressure has reduced. By what factor has it reduced? It has reduced by a factor of rho u square. U square in this case is z dot square. This is only, by the way, this is only, all of this is only true when this is only for a brief moment. Okay, this will not be valid So this will appear only in the early the inertial region. Okay, like over here. But you have basically after a certain height, the speed has decreased. Therefore, there is no real benefit from this decrease in pressure. The decrease in pressure is marginal. So the argument is as follows: when the fluid is actually rising, its pressure is actually lowered, and as a result, the atmosphere can actually push it down. That's one way to think about it. Okay. I'll give you a completely different analogy, which is not related to there's a very extremely high speed analogy. Okay, this is that you encounter in high speed flows. For example, if you were to look at, let's say, a rocket motor. Okay, in a rocket motor, the gas is exiting at very high speeds. Agreed?
Yes, sir. Yes, sir.
Now, if the pressure at which the fluid is exiting is not, it's exiting at very high speed, but you are also starting with a very high pressure gas. So you have a high pressure gas here. So this is P is very high here. And P is low here. Now, if this pressure is not equivalent to the atmospheric pressure, it's lower than the atmospheric pressure, then what happens is when it exits, the gas actually comes inwards. Simply because atmosphere is actually pushing it inwards. But if the pressure that of exit, this is the P exit. So what you're actually simultaneously doing is you're doing two things here. The pressure in the combustion chamber is very large, and as it exits the nozzle, its pressure is continuously decreasing. Okay, and rocket engineers basically achieve this by basically expanding the gas to lower the pressure. The idea is that you want to lower the pressure and bring it as close to the atmospheric pressure possible. If you are not able, if the pressure actually exceeds and goes further below the atmospheric pressure, meaning the pressure drop, you start off with very high pressure, but if the pressure falls below the atmospheric pressure, and why would pressure drop below the atmospheric pressure? It could drop simply because it's moving at very high speeds by Bernoulli's. And if its pressure drops below the atmospheric pressure by Bernoulli's, if P exit is lower than P naught, it actually is pushed. The atmosphere actually pushes it in. In the same way, when fluid is rising to the capillary tube, because its pressure actually lowers, okay, and that lowering of pressure makes the atmospheric pressure effective to push it back up. So the very act of motion will basically create a suction pressure backwards. Is this clear?
Yes, sir. Yes, sir. I can relate now. Yes, sir. I got it. Yes, sir, got it.
Yeah, this is, but I do understand that this is one of the trickiest ones.
Yes, sir. Yes, sir. Now we can relate. Actually, thank you. Yes, yes.
Okay. So, yeah. Okay. Anybody else was joined? So if there are no more questions, shall we call it a day?
Just one thing I wanted to ask. Sure. From from the discussion perspective, you referred us to a lecture by John Bush of MIT in the lecture that you have referenced them also. I just visited that website. So they were working on. There was this on the front page of one of the magazines. They have taken a photo of an insect which is floating on water. So sir, I just wanted to ask. We have also seen insects floating on water. Is that due to the hydrophobic surface on the surface of the mosquito's leg, or is it due to that some kind of lotus effect we were discussing in the lecture previously? So what is it due to, like insects floating on?
Okay. So in NPTEL lectures, I felt the content that I'm teaching is already becoming too. Uh, there's a lot of material that I had to cover, so I chose to skip this topic of floating particles. Okay. If you were to think about it this way, if you were to put a small particle on a liquid, it will float. Now you ask yourself, why is it actually floating? Okay. Now this particle, by the way, unlike this is effectively what surface tension is doing is it is amending the Archimedes principle. Okay. So Archimedes principle essentially says an object can float provided the weight of the object is lower than the amount of fluid it displaces. Is that correct?
Yes, sir, it is.
Okay. So now um, uh, there's no disagreement with it, but this if you think about solid particles, if you think of a solid particle, let's say I have in front of me I have a block. Okay. So if you look at a block like this, and let's say it's assume a metal block, this block can never actually float by Archimedes principle if its density is heavier than that of water. Okay, because the moment I put it in water, it will go a little bit down, and then the moment it goes a little bit down, you find out what is the force of what is the weight of the liquid displaced and what is the weight of the object. The weight of the object will be larger. So the object will continue to go down and down and down until it is fully submerged, and it will eventually sink. Okay, but if you start going into small scales, then you have surface tension forces. The surface tension forces is not that different from what you've seen in capillary rise. In capillary rise, there is a meniscus there, and there is a little meniscus where the curve interface basically bends and when it meets the walls. And that bending will create bending of the surface will create an additional surface tension force, correct? At the contact line. The same thing is happening to these little insects. These are, you would have seen, I think the Professor John Bush and many others have done some absolutely wonderful experiments, and Professor John Bush is a pioneer in this field. He has done some absolutely pioneering work. There's a very nice, if I recall, there's a very nice paper, I think in Annual Review of Fluid Mechanics, where he has discussed these kinds of problems. So if you have a tiny insect, let's say a water strider that is sitting on water, its legs are basically in contact with the surface of water. So it experiences a surface tension force. And the more the legs, the merrier, because you can actually, if you have 6 legs, you have 6 times the surface tension force of one single leg. And then if this collective force actually increases, is larger than the weight of the object, weight of the insect, it will float. So you can actually do an experiment. It's a bit of a cruel experiment. I wouldn't recommend it, but you can do it for scientific purposes. If you find in a water body, if you find such water striders, what you can do is if you add a little bit of soap or surfactants, what it does is the soap surfactants will lower the surface tension. You will find that these objects, the insects will sink. They will drown. You can also try this. You can do with inanimate objects. Let's say you take a tiny needle. It could be a stainless steel needle or metallic needle. You can take a shaving blade. You can all make them float on surface. Now a stainless steel blade, like what you would find in a shaving razor, it's obviously its density is obviously much higher than water. But if you carefully put it on the surface of water, you can make it float. Now you try this experiment. This is not that this is the same reason why water striders are able to, insects like this are able to stay afloat on top of water. It's surface tension effects. But now you add a little bit of soap and see what happens. The moment you add soap, what you're really doing is you're lowering the surface tension. You have to, of course, add soap very carefully such that you're not generating a large scale flow in the system. I mean, in the process of adding soap. Okay, you want to observe the effect of surface tension variation. the lower you want to see what is the effect of surface tension and what happens when you lower the surface tension value. And I would leave it you to try this experiment and you will see what happens.
This is indeed very interesting, sir. Okay, thank you. I'll try this one.
Yeah, you can try it with you have to of course start off with objects which are slightly heavier than water. Okay, you don't want to try with something like a small thermocol ball. It will anyway float on the surface of water. Because its density is so light. And even if you take a very tiny thermocol bead, it will float, and surface tension maybe perhaps it will make it float even up. But if you lower the surface tension, you may not be able to detect much by the naked eye. Okay. So it's easier to test this kind of an idea with an object which is to begin with heavier than the denser than the object, like and surface tension is the main force which is holding it up. All right. So, well, if there are no more questions, then maybe we'll end the session.
Thank you, sir. Thank you.
Yeah. Okay. So I request the NPTEL team to end the live session as well.
Thank you, sir.
Thank you, sir.
Thank you. Thank you. Can we end the live session?